Hi class, this is an example problem for Unit 2.3. Unit 2.3 deals with the dot product, and the dot product, we really use it for two things. One is to find the angle between two vectors, and the other is to find, basically project a vector in the direction of another vector, or to basically find out how much directionality two vectors share, which I know is kind of a maybe a difficult concept to understand at first, but as you go through some problems, hopefully it makes more sense. So in this case, I'm going to try to demonstrate both of those applications of the dot product, and I'm going to use problem 2-127 in the book. This is the 13th edition, and this is what the problem looks like. It's this image right here. So hopefully you can kind of look at that and visualize what I'm trying to draw. It's always a little bit tricky to draw three-dimensional problems on the whiteboard. But so essentially what we have is we have this pipe, and on this pipe there are two forces being applied. There's force one, which is this guy, and for him we're given the azimuth and elevation angle that we've been learning about. And he is pointing in the positive x direction, positive y direction, and in the negative z direction. So he's down in this quadrant over here. And then F2, he's pointing, for him, we're given two of the coordinate direction angles. We're not given the third, but we can find that since we have two. And he's pointing in the positive y direction, the positive z direction, but in the negative x direction. And so we're given those means of determining those vectors. And what we're asked to find is the angle theta between the two cables attached to the pipe, or the two vectors. And then we're also going to find the magnitude of the projection of F1 along the axis of F2. So we're going to do both of those and hopefully kind of demonstrate why the dot product is useful and how to use it. So make sure to do this in my blue pen because that's my best pen right now. So for the solution, first thing I often like to do is to just write down what is the kind of final equation I'm going to work towards. So in this case, the final equation that I'm really working towards looks something like this. This is just our basic dot product equation. So we know that the F1 vector dotted with the F2 vector is going to equal the F1 magnitude times F2 magnitude times the cosine of the angle between them. So ultimately, we're trying to find this. We're given these magnitudes. F1 has a magnitude of 30 pounds, F2 has a magnitude of 25 pounds. And we have the means of finding these two, but we got to do those and find F1 and F2 first. So let's get to that. I'm going to label this as equation one, just so we can easily refer back to it later once we've found F1 and F2. So first, let's find F1. So like I said, we're given the azimuth and elevation angles for this. In this case, both of those angles are 30, and it's being measured off the y-axis. The azimuth is being measured off the y-axis. So that means that when I set this up, F1 is going to be the x component is going to be the magnitude, which is 30 times the cosine of 30. That projects it into the xy plane, and then times the sine of 30, because we're being measured, the azimuth is measured from the y-axis. That gets us basically this length right here, and that is in the I direction. And let's see, and it's positive x, and it's also positive y. So we get 30. Similarly, it's cosine 30, and I apologize for my handwriting. And then cosine 30. And that gives us the y direction. And then it's in the negative z direction, so it's minus 30 sine 30. Hopefully using azimuth and elevation is nothing new to you now at this point. So when I simplify that out, I get that F1 equals 13 in the x plus 22.5 in the y minus 15 in the j direction. So I'm going to label this 2, so that we can come back to that here in a little bit. And now for F2, we are given the coordinate direction angles. So let's see, if I were to F2 going to equal 25 cosine alpha, which we don't have yet, plus 25 cosine 60. That's it's not very good. I and j hats plus 25 cosine 60 for the oops, not the y direction, for the z direction. We're going to come back to this in a little bit because we got to find alpha before we can do anything here. So we got to find alpha. Now, to find alpha, we're going to use our direction angle identity. And in this one, we have to be just a little bit careful, because if we just blindly apply the identity, we're actually going to wind up with the wrong alpha. So remember that the square root, the sum of the square roots of a coordinate direction angle, of the coordinate direction angles, equals 1. And so I can write it this cosine alpha squared plus cosine 60 squared plus cosine 60 cosine 60 squared equals 1. And this is where we got to be careful, right? Because the inside of these can be plus or minus. This, once it gets squared, it doesn't matter. It's going to be plus. So in this case, we know that this vector points in the negative x direction, right? Because they gave us this little indication that it's pointing that way. So it's actually going to be minus. And if we didn't include that minus, then we would find a vector that was pointing out here, where they're all positive. And that would be incorrect. So basically, there's two solutions to this problem, depending on whether we assume the inside of this square term is positive or negative. In this case, since we know it's in the negative x direction, we know it's got to be negative. So if we go ahead and solve it from there, it's cosine of 60 squared ends up being 0.25. So eventually we wind up with negative cosine alpha is going to equal to the square root of 0.5. I'm skipping a couple of math steps to save some space. And then I end up getting, if I solve it out from here, I trust your ability to solve it, I end up getting that alpha is going to equal 135 degrees. If we hadn't included the negative sign, we would have gotten alpha equals 45 degrees. And remember that the coordinate direction angles are always measured from the positive x, y, or z axis. So alpha equals 135 degrees. I'm going to call this item 4. I'm just going to make a note that we're subbing in 4 into 3 here. And when we do that, we end up getting that. I'm going to skip a little bit of math, simplification really. That F2 is going to equal negative 17.68 I plus 12.5 J plus 12.5 K hat. All right, we'll call this number 5. Now we're going to sub 2, which is the F1 value, and 5 back into our original equation. Now we have everything we need to solve for this guy over here. So when I do that, right, so I'm taking the dot products of these two guys, and when you take the dot product of two vectors, you multiply the x's, you multiply the y's, you multiply the z's, and your answer is going to be a scalar. It's no longer going to be a vector. So it's going to look something like 13 times negative 17.68. So those are my x's, plus 22.5 times 12.5, those are my y's, and then plus -15 times 12.5, so that's this part. And then the magnitudes, which we were given at the beginning, so the magnitudes are 30 times 25 cosine theta, right? So the x's are my two vectors, the y's are my two vectors, the z's are my two vectors just multiplied by each other. The magnitude of f1, magnitude of f2, cosine theta. And now if I do all the math, I wind up with the left side gives me it's -1, 36.09. The right side gave me 750. I'm just going to divide it over now. That's going to equal cosine theta. And then I take the inverse cosine of that, and I get that theta equals 100.45 degrees. And that would be the answer to part 1. So hopefully that made some sense. The cool thing with this, something just to keep in mind is, if you, actually no, never. So I'll talk about what I was about to say in the next part. But yeah, so that's how we can use the dot product to find the angle between two vectors. So for the next part, we're going to find the magnitude of the projection of f1 along the axis of f2. And I'm going to need some space, so I do need to keep track of some of this information now. So I'm just going to write some of these important values so I know that, so we can keep track of them and reference them. So f1, keep track of it down here, is 13, 22.5. I had a bigger whiteboard, this wouldn't be necessary. Hopefully in future videos, I'm working on a slightly bigger board. And then F2, so see that, okay. Again, apologies for the bad handwriting. Left-handed people and whiteboards are mortal enemies. I can barely write without erasing what I just wrote. Plus 12.5. 12.5. Okay, so we're going to refer to those here in the second part. So I want to make sure that we don't erase all that. But I'm going to erase this up here. Okay, so when we are, so now we're going to project F1 along the axis of F2. When we do this, basically what you do is you do something like this. So I'm going to say magnitude of F1 projected along axis 2. That's just, I'll notate it like that. And the way I'm going to do this is I'm going to take my F1 vector and I'm going to dot product it with a unit vector, the unit vector of F2. So that will effectively tell me how much of force vector 1 is in the direction of force vector 2, right? So unit vectors have a magnitude of 1 and they only convey direction. So we need to find unit vector 2. So let's call this equation 6. Unit vector 2, and then we can just refer back down to here. So it's going to be minus 17.68 plus 12.5 J plus 12.5 K, and the magnitude is 25. So I do the math and I get minus 0.707 plus 0.5. So this is still going to be a vector plus 0.5. And we probably could have already figured this out because this is the same as, let me just point this out, right? This is the same as cosine, right, 135 cosine 60. Right, so coordinate direction angles, those are our coordinate direction angles. They basically tell us the unit vector. So kind of a good thing to remember that we basically did already have that information. Right, so we could either do it this way, or for the coordinate direction angles, just take the cosines of them, and we end up with the unit vector. So that's convenient. And then all we got to do is dot this unit vector with this. So let's see if I called this 7. We're just going to say we're going to put 7 into 6. And what we end up with is that F1, 2 is going to be 13 times negatives 0.707 plus 22.5 times 0.5 plus negative 15 times 0.5. And when I do the math, that gets me a value of negative 5.44 pounds. So that's another final answer. And so one thing you should always check, your projection should always be equal to or less than or equal to your original magnitude. So my original magnitude for F1 was 30 pounds. This value had, the magnitude of this value better be less than 30. The maximum it can be is 30 if it was projected along an axis that was parallel to F1, then it would be 30. It could be 0 if we're trying to project it along an axis that's perpendicular to it, right? Perpendicular, they share no directionality, and the dot product will be 0 in that case. But typically it's going to be somewhere in between its original magnitude and 0. In this case, the negative just means that it'd be something kind of like this, where it's if you were to project it, it'd be pointing in the negative in the opposite direction of the vector that you're trying to find, whose axis you're trying to project it onto. So that tells us that. And then say, the problem asks us for not just the magnitude, but the vector, or F1 projected along axis to the vector form. Then I just take this magnitude and multiply it by this unit vector again. So if I were to do that, right, I said vector version of force 1 projected along force 2, it equals negative 5.44 unit vector 2, which would end up giving me 3.85 I hat minus 2.72 j hat minus 2.72 j hat. So that's that. That's the dot product in a nutshell. Everything that we'll do with it will pretty much be an application of one of these two things. Either using it to find an angle or using it to find how much of a vector is in the direction of another vector. So hopefully that proves helpful as you're working your way through these problems. And as always, reach out to me if you have any questions. Thank you.